All right, thank you. Thanks for the intro. Thanks everyone for joining the session. My name is Adarsh Shah, and today I'm going to talk about continuous delivery for machine learning systems. What this is how to deploy machine learning systems to production safely and quickly in a sustainable way. This talk is based on my experience working with continuous delivery over the years with traditional software, and then applying those same continuous delivery principles and practices to machine learning, which has been in the last few years. So I'll be using some examples from my experience and also kind of taking in the knowledge of continuous delivery, working with that for using traditional software for years. All right, so let's get started. All right, so one of the known truths of the machine learning world is that it takes a lot longer to deploy machine learning models to production than to develop it. According to the paper Hidden Technical Debt in Machine Learning Systems, only a small fraction of real-world ML systems are composed of the ML code, as shown by the small black box in the middle. The required surrounding infrastructure is vast and complex. So as you can see, configuration, data collection, data verification, infrastructure monitoring, there's so much surrounding infrastructure that's needed for machine learning code to run. The small black box that you see that's the only machine learning code, right? So everything else surrounding that is what makes an ML system run in production. So before we get started, I'm going to quickly go through what's the difference between traditional software and machine learning first. So on the left, as you can see, you write a program where you have your logic, and then you have your data for your traditional software. And then that goes through the compute, and then you get your results, right? So pretty simple. Anytime you have to change something, you change your program, or if there is a change in the data, you change the data, either the schema or the data itself, and then you go through the compute again and get the results. In terms of machine learning, you actually provide the desired results and the training data, right? So you provide this data that you know what the results are supposed to be. It goes through a training process, which in terms gives you the model that gets trained based on the training code, the desired results, and the training data. Once you get that model, you feed it into the program. This program here could be your web application, your desktop application, your API, and that program, along with the live data in production, starts doing predictions, and it starts giving you results like it would in a traditional software in production, but it uses this model that's trained, and then it gives you the result. This process on the left, as you can see, is a little different for machine learning than traditional software. You're actually not writing the whole program that's running in production. You are using this model that gets trained to do prediction with live data. One thing, though, I have to say is that most of the principles and practices of traditional software still applies to machine learning, right? But there are certain unique challenges, and we'll talk about those unique challenges in a bit. So here's the three different phases of machine learning. The reason I'm talking about this is because we look at the challenges in each phase, and then we look at how to kind of resolve them using continuous delivery. So the first one on the left is data management. Data is really critical to machine learning. The quality of data kind of defines the quality of the model that you have. So you have to do data acquisition and data preparation, right? So you're getting data from various sources. This is typically the training data that we talked about. Once you get that data, you kind of feed it into the experimentation phase. this experimentation phase, you do the model development, right? So you write the training code. Data scientists usually pick a model architecture that they want to use, and they kind of keep on experimenting with various data, various architectures, various training code, and see whether they reach a certain accuracy level. So there's this validation step. Where if they don't reach the accuracy level, they keep on going and keep trying, various things until they reach that accuracy that they expect out of the model. Once they start getting that, the model along with the program gets deployed to production. And then it starts doing predictions, as we saw in the previous diagram as well. But you keep monitoring and seeing if the performance of the model in production is the same as expected, right? If it starts degrading or you have a data drift, you might have to retrain the model or fix the data drift issue and kind of go back again, right? But the idea is you train the model and then deploy to production, it starts doing predictions. Now let's look at some of the challenges with machine learning that are unique to machine learning. I'm not going to talk about traditional software challenges, but these are unique to machine learning. So the first phase, data management, right? You typically work with large data sets with machine learning. Data sets are typically hundreds of gigabytes or even larger in size, right? In terabytes. So you have to keep that in mind because you can't do things manually because it'll be time consuming if you have to do it again and again. If you make a mistake, it's just too much time, right? You also have to think about location of the data, right? So since the data sets are large, usually moving them around is not easy. It's costly, it's time consuming, and also you have to think about compliance reasons. You might actually can't take the data out of a location because of certain compliance, like HIPAA or PII or other compliance reasons. And as I mentioned earlier, data quality is pretty important because that kind of drives the model quality. If the quality of data is not as good, you would not get good quality models. So focusing on the quality, making sure that it's really good is important. And then tracking data sets. As I mentioned in the experimentation phase, that if you want to try and see different data sets, which one performs better in terms of training, then you should be able to go back to a previous version if that one is better than the current version. So tracking those, versioning those helps in going back and forth during experimentation phase. And then anytime we talk about data, security and compliance is always important, right? So making sure that you don't have any data leaks or you're complying to all the regulations that you have to, including GDPR, HIPAA, or any other based on the region where you are and the industry that you're working in and you need to comply to. Next one being experimentation phase. So as I mentioned, data scientists do a lot of research and experimentation, and their focus is trying to find the right combination. They're not actually looking at writing production quality code, right? So a lot of times what happens is you go through this experimentation and research phase, and you have a good model and training code, but the quality of the data, the quality of the code itself that's going to go to production is not high quality. So you have to be cognizant of this and make sure that before you go to production, you have the high quality code that you would want to run in production. And then because you're working with large data sets, and typically training process takes time. It takes, in some cases, hours or even days. So one of the examples I'll give is I was working with these data scientists for one of the neural networks, and training took up to 3 days, right? So they would start the training, they would go about doing other things, and then kind of keep track of things. If something went wrong, they have to troubleshoot it, fix it, and restart the training. But it took time, one of the other examples is for a full build of Tesla autopilot neural networks, it takes up to 70,000 GPU hours to train. This is as per their website. That doesn't mean, by the way, it takes 70,000 hours. It's just that many GPU hours. So if you have more GPU, the time will be less. But still, you get a sense of how much time typically it takes. And then you have to evaluate the model accuracy. And if it doesn't match, you kind of go through the process again. But you need to have a step where you can say that this matches, the model matches the accuracy that we are expecting. And then, like tracking data, you should track experiments as well, right? So your training code, your model architecture. So having a process where you track those things and you can go back to it if and when needed is helpful. And then last but not the least is infrastructure requirements. So as I mentioned in the Tesla example, things like GPU and high density cores in certain cases are used during training process, and even in production during predictions phase helps you speed up things, helps you in solving the problems faster. So there are certain specific infrastructure requirements. Now, one thing here is GPU hardware or high density core hardware is expensive, right? So either you're buying those hardware, which is expensive, or if you're provisioning stuff in cloud, those costs can add up, right? So you have to have right processes to provision, deprovision your infrastructure when you don't need it. So again, keeping that in mind is helpful. The next stage is production deployment, right? So there are usually two types of predictions. There's an offline prediction and an online prediction. In the offline prediction, you can think of it as a batch processing or a batch prediction, which basically means that you're not taking in live data and doing real-time processing, but it's mainly in batches. And once the prediction is done, you kind of send the results. And the second one is online, which is more real-time, right? So you're getting real data, live data, and then you're processing and giving the results back, right? So keeping those in mind, as in batch processing, you should be supporting long-running processes. In terms of real-time, you have to support, you need to think about the performance, the time it takes to get the results back and stuff like that. And then continuously monitoring the performance of your model, making sure if it goes below the threshold that you have, you alert your teams, and then providing all the tool sets to kind of troubleshoot and kind of fix the issues as well. All right, so those were the challenges. Now I will go through continuous delivery, and then we look at how to apply the continuous delivery principles to machine learning. So I'm not going to read the definition, but basically this is from the book, a continuous delivery book written 10 years ago by Jez Humble and Dave Foley. If you haven't read it, it's still relevant. I still refer to it. But yeah, as you can see in the bold, it says safely and quickly in a sustainable way. So deploying your features in a safe and quick way is important, and continuous delivery helps you do that. So I'm going to compare batch processing and single piece flow here. So single piece flow is what is continuous delivery. On the left, as you can see, they're processing things in batches. So if there is an issue when you integrate batch one with another batch, you might find issues, and that might be too late, right? So you're kind of delaying the process of integrating things, and it takes time, and it takes, in some cases, that will cost you money and time because you find issues later. Also, finding root causes is very difficult because it might be a while before you actually find the issue, right? On the right, you can see it's a single piece flow. You take one thing, take it to finish, right, to a finished product, and you find the root cause right away. If you're integrating piece one with piece two, right away, you know if they don't fit together, right, for example. So second, the single piece flow is basically continuous delivery. And I'm not going to talk too much in detail, but if you want to read more about Ford Motors and Toyota, right? How Toyota used to do things and Ford Motors used to do things in mass production back in 1930s. And Toyota started doing the single piece flow. So read about it more if you're interested. So first step to continuous delivery is continuous integration. If you're doing nothing, that's where you start. So continuous integration is a software development practice where members of a team integrate their work frequently. Usually each person integrates at least daily, leading to multiple integrations per day, according to Martin Fowler's blog. So here, basically, each integration is verified by an automated build, including tests, to detect integration errors as quickly as possible, right? So pretty important for continuous delivery, and as I said, a first step to continuous delivery. And what are the principles of continuous delivery? So first one being build quality in. So according to Edward Deming, who's one of the key figures in the lean movement, who offered these 14 principles of management, right? The second principle there says that cease dependence of inspection to achieve quality. Eliminate the need for inspection on a mass basis by building quality into the product in the first place, right? So what he said is, don't look at this heavy inspection phase towards the end, but build the quality into the product itself, right? So do your things, your testing and other things as part of your flow itself, your product itself, right? So you're not doing this heavy inspection phase at the end. Second one being work in small batches. As I mentioned earlier, doing single piece flow and getting faster feedback is helpful in finding issues. And this is pretty important. And there is a word for this called jidoka, right, in Japanese, which means that automation with a human touch. So computers perform repetitive tasks, right? They are good at that. We should use computers for that. But people solve problems, right? So you need automation, but you need that human touch as well to kind of solve problems. Next one being Kaizen, right? So continuously look to improve and see. I'm sure all of you kind of try to improve on what you do and try to kind of solve the problems and look at various ways for improvement continuously. And then another important one that I always, when I work with various organizations, kind of see them saying, it is somebody else's problem. But according to continuous delivery principle, it says it's everyone's problem, right? Don't say that it's not your problem, but basically work with various teams to kind of solve the problem together. Okay, so now that we have looked at, we started by looking at what is machine learning and the phases. We looked at continuous delivery. Now actually look at how do we apply those continuous delivery principles to machine learning. So for the first phase, for the data management phase, right, one of the things that you can do is start building automated data pipelines, right? So as I mentioned, large data sets, you have to look at high quality data, security compliance, tracking the versions of data, all of those issues. And also collaboration. One of the biggest thing about this is it allows you to collaborate with various teams, like data scientists, security teams, compliance teams, and other things, right? So let's look at this. So as from the left we go, we have different data sources because in a lot of cases, you kind of pull data from various sources to kind of use that, bring it together, and pass it to the training step. So first step is data acquisition, right? So you need to have a way to acquire data from various sources, then validate it, make sure that the schema, but also taking it further, make sure that your data is uh, uh, in a valid state. So one example here I would give is when I was working with these data scientists, they were getting these images from a third party, and suddenly we started getting some batches where the caption of the image was in a different language, right? So we had to kind of validate that. And then if it was in a different language, we had to actually translate it. So that brings us to the third step, which is the data preparation, right? So you have to do things like data normalization, data transformation, any feature extraction, all of that to make sure that data is in a good state to be passed to the training process. And then you kind of do it for all the various data sources. And then this is a critical step here, right? You're testing, but especially for bias and fairness, right? A lot of companies, especially we have seen with credit card companies recently, is that they are biased against a certain race or gender or religion, which is not fair, right? So having and making sure that this bias is not introduced into the model by the way of data is critical, right? So you kind of do those testings with the data even before you train your data set, train your model. So yeah, having that testing is pretty critical. And then doing your security and compliance tests, right? So you can automate some of that as well, write compliance as code, and then use various tools that are available for security to make sure that your data is secure. And then that becomes your training data set. You version that data to make sure that if you have to go back, you can go back. And then kind of that feeds it into the training process. The next one is continuous integration, right? For your training code. So you write your training code, you make sure that you do your CI, right? This is a typical CI, right? You kind of, once you merge it to your main branch, you kind of go through your static code analysis, unit testing, linting, all of that, right? To make sure that even your training code is of good quality, because if you don't have that, the maintenance is a nightmare, and then also, that doesn't help you kind of train the right model. Then the training process itself. So we got the data pipeline, we got the training code that feeds it, and data scientists kind of trigger the training process. You got to make sure that you have, in cases where you need GPU and high density cores and they are expensive, if you automate provisioning and deprovisioning of your infrastructure, that'll help you save costs. So having those kind of tests will help. Like having that kind of automation will help there. So make sure that you add that along with accuracy evaluation and testing, right, for bias and fairness. So we did talk about bias and fairness for the data phase, right, when we were doing the data management. But it's also important to have bias and fairness in the training process to make sure that the trained model is not biased. And then having monitoring alerting for your training phase, right? So as I mentioned, training takes time, sometimes days. And if it takes days, then you got to be troubleshooting and be available. Monitor the progress. If things goes wrong, then you kind of alert your team so they can look at it, right? So provide logs so they can troubleshoot the issue, and other tools as well, right? So they can troubleshoot it, restart the training if needed, or continue the training after fixing the issue. And then that gives you the model that then feeds, gets deployed to production. Okay, so we talked about continuous integration for the training code. let's talk about continuous integration for the application code, right? So this application code is the program that we talked about gets deployed to production, right? So you write that, and again, this is a typical CI, so I'm not going to go through each step, but basically, like for training process, you have these steps like static code analysis, unit testing, linting, security scans, things like that. But here, one thing is different is you might actually want to provision an ephemeral environment, ephemeral being a temporary environment, and then kind of test your code, right? Run your integration tests, and then kind of tag that artifact and push it to artifact repository. So yeah, that's your CI that helps you keep the quality of the application code and finding issues faster for your application code, right? And as you can see on the left, on the training step, right, you have the model that kind of feeds it into the CI as well. So your model is part of the artifact that gets generated. So let's bring it all together, right? All the various phases and what we looked at and how they fit in together. So data pipeline, right? So data pipeline steps, if you have that automated data pipeline, that'll help you eliminate issues that we looked at, and that'll feed it into the training data, become the training data set. Then we looked at the CI for the training code, and that CI training code, it also feeds it into the training process, right? So your training data set, your training code, and then there is any environment configuration as well. That gives you your model. That model then feeds it into the CI of your application code, where you use the artifact that gets generated from that step to kind of deploy to production. You run your smoke test and do all of that, and then that you keep monitoring and alerting, right? So kind of bringing various pieces together. And again, one of the key things here are the people, and let's talk about that a little bit. So machine learning roles that are there, I'm not going to go through these because I know I'm running out of time, but these are typical machine learning roles. But let's look at team structure considerations here. So cross-functional team is still good here, right? So kind of you have new roles like data scientists and machine learning engineers, but still cross-functional team where you have various roles brought together to build a common product is still the best approach. If you can't do that, have a separate data science team. That's even possible, but there you have to make sure that they collaborate with the various teams that are there, right? And then having a platform engineering team, that's another one. This is more specific to machine learning, but basically a platform engineering team that kind of builds a platform. Again, they have to look at building it in a self-service way so that they are not like, ticket-based system where the other teams create a ticket and they do the work, but it's more self-service. So that the data scientists and other application development teams kind of use the platform in a self-service way to serve themselves. So yeah, I mean, I would love to spend more time here, but we're running out of time. So if you have any questions about these, I'm happy to answer later. Here are some references that will be available part of my slides. Actually, you can see the URL to the deck at the bottom in the footer if you want that. Here are some book recommendations. I mean, continuous delivery book we talked about. But there are some Toyota Kara books that talk about some Toyota management principles that we learn a lot from. And then, yeah, that's it. My name is Adarsh Shah. Thanks for listening. And if you have any questions about cricket, whiskey, or maybe if you have some questions about the talk as well, happy to answer. That's all. Thanks for listening.